Hello everyone. So the topic for today would be about vector functions and space curves. Vector valued functions. In general, a function is a rule that assigns to each element in the domain an element in the range. So for every point in the domain, there is an equivalent value in the range. A vector valued function or a vector function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. We are most interested in vector functions R whose values are three-dimensional vectors, meaning there would be three components: x equal to f of t, y equal to g of t, and z equal to h of t. This means that for every number t in the domain of R, there is a unique vector v sub 3 denoted by r of t. If f of t, g of t, and h of t are components of the vectors r of t, then f, g, and h are real valued functions called the component functions of R. And we can write it in terms of components r of t is equal to the components x equal to f of t, the second component y equal to g of t, and the third component z equal to h of t. Or we can express it in terms of unit vectors f of t, I, plus g of t, j, plus h of t, k. We use the letters t to denote the independent variable because it represents time in most applications of vector functions. Let us consider the function r of t with the components t cubed, ln of 3 minus t, and square root of t. Then the component functions are, for the first component, we have f of t equal to t cubed, g of t is equal to ln of 3 minus t for the second component, h of t is equal to square root of t. By our usual convention, the domain of R consists of all values of t for which the expression for R of t is defined, meaning our initial assessment is that the domain of the function would be the set of all real numbers. After that, we're going to reduce the number or we're going to reduce or limit the domain of the function, removing some parts for which the function would not exist. The expression t cubed is defined over all points in the real number. However, for ln of 3 minus t, it would only be solvable, or it would only be having a value when 3 minus t is greater than 0, because for ln the argument must be positive. For square root of t must be greater than or equal to 0 for even index radical. So they are all defined when 3 minus t is greater than 0 and t is greater than or equal to 0. Checking for the intersection of all real numbers, 3 minus t greater than 0 and t greater than or equal to 0, we're going to have the domain of R to be the set of points in the interval from 0 inclusive up to 3. The next thing that we would be evaluating would be limits, and we're going to inspect or check if the function is continuous. The limit of a vector function R is defined by taking the limits of its component functions as follows. If r of t is given by f of t, g of t, and h of t, then the limit of r of t as t approach a is equal to the limit of f of t as t approach a, the limit of g of t as t approach a, and the limit of h of t as t approach a, provided the limits of the component functions exist. The limit of vector functions obey the same rules as limits of real-valued functions. For example, we are asked to find the limit of r of t as t approach 0, where r of t is equal to 1 plus t cube I plus t e to the negative tj plus sine t over t k. According to our definition, the limit of r is a vector whose components are the limit of the component functions of r. So the limit of r of t as t approach 0. So what we can do is to apply the intuitive approach wherein we are going to plug in, we're going to try to check whether the limit would exist as t is plugged in to the variable t. So 1 plus 0 cube would be 0. There would be no violation to the left and right of 0. So 1 plus 0 is 0. So 1 plus 0 is 1 rather. So this would be 1i. So we will be having I. And the limit of t e to the negative t as t approach 0 would be 0 e to the negative 0. So it would be approaching 0. There would be no mathematical errors applying this to both sides of the limits as well. So it would exist and it is approaching 0. J. And then for the third component, we're going to have sine t over t as t approach 0. So it would now be the limit of sine t over t as t approach 0. So as t approach 0, this would be following the rules for squeeze theorem. Under squeeze theorem, there would be two functions, sine t over t and 1 minus cosine t over t. As t approach 0, this limit would be approaching 1. And this is approaching 0 as t approach 0. So meaning this would be approaching 1 and then k. So we have I plus k. Now you can also think of it as a different function under indeterminate forms. And in indeterminate form, you can apply L'Hopital's rule. So we differentiate numerator and divide it by the derivative of the denominator. So that would be cosine t over 1. And that would be cosine of 0, which is 1. So 1k. A vector function r is continuous at a if the limit of r of t as t approach a is equal to r of a. In definition 1, we see that r is continuous at a if and only if the components f, g, and h are also continuous at a. This is somewhat similar to the concept of continuity under functions, that the limit of f as t approach a from the left must be equal to the limit of f as t approach a from the right. So this is the limit exists. Similarly, so we must first check whether the limit exists and f of a exists, and the limit of f as t approach a must be equal to the limit must be equal to f of a. Now let's have space curves. There is a close connection between continuous vector functions and space curves. So what are we going to trace, or what figure are we going to develop from this three-component vector functions. So it would be a space curve. Suppose that f, g, and h are continuous real-valued function on an interval I. Then, the set C of all points x, y, z in space, where x is f of t, y is g of t, and z is equal to h of t, and t varies throughout the interval I is called a space curve. The equation in 2 are called parametric equation of C, and T is called a parameter. We can think of C as being traced out by a moving particle whose position at time t is f of t, g of t, and h of t. So we now consider the vector function r of t equal to a vector with components f of t, g of t, and h of t. Then r of t is a position vector of the point f of t, g of t, and h of t on C. So just for our example to be more concrete, you can consider your projectile motion as a function of t equal to a function along the horizontal x of t and y of t vertically. So we can have the horizontal motion x naught plus vox times t, vox of t times t, and then y naught plus v naught y of t times t minus 1/2 gt squared. So we have a horizontal component, so we can write it down as x naught plus v naught cosine theta t, y naught plus v naught sine theta t minus 1/2 gt squared. So this is a uniform motion, while this one is the equation for free fall. Thus, any continuous vector function R defines a space curve C that is traced out by the tip of the moving vector R of t as shown in the figure. So it would be moving along X, along Y, and along Z. So the motion is governed by, so you have a motion along X, along Y, and along Z. So for every point, there is a movement along these three directions. Sketch the curve whose vector equation is given by r of t is equal to cosine t I plus sine t j plus tk. The parametric equation for this curve are given by x equal to cosine t, y equal to sine t, and z equal to t. The first two components can be combined using Pythagorean relations cosine squared theta plus sine squared theta equal to 1. So with this, we can say that x squared plus y squared is equal to 1. The curve must lie on a circular cylinder defined by x squared plus y squared equal to 1. So the cross section is a circle with center at the origin 0, 0, and the radius is 1. It would be projected on the z-axis. So when the circle is projected or pulled in the z-axis, it would be a cylinder. The point xyz lies directly above the point xy0, which moves counterclockwise around the circle x squared plus y squared equal to 1 in the xy plane. So the projection of the curve into the xy plane has the vector equation r of t cosine t sine t 0. Since z is equal to t, the curve spirals upward the cylinder as t increases. The curve shown in figure 2 is called a helix. The corkscrew shape of the helix in example 4 is familiar from its occurrence in coiled springs. It also occurs in the model for deoxyribonucleic acid, the, the genetic material of living cells. In 1953, James Watson and Francis Crick showed the structure of the DNA molecule is that of two linked parallel helices that are intertwined as shown in the figure. Now let's draw space curves using technology. So space curves are inherently more difficult to draw by hand than plane curves. So it would be quite impossible for us to draw it manually. It is possible, but it would be a challenge for us to sketch the curves. For instance, figure 8 shows a computer-generated graphs of the curve with the parametric equation x equal to 4 plus sine 20t times cosine t, y equal to 4 sine 20t times sine t, and z is equal to cosine 20t. This is called a toroidal spiral because it lies on a torus. If we are going to apply this in MATLAB, the code would be t equal to, so maybe we can try from 0 to 100. And then we apply semicolon so that it would no longer be displaying all of the points. Now I want a smaller interval, so we can have 0 to 100 and we can apply 0.01 as the interval. So it would be 0, 0.01, 0.02, 0.03, 99.99 until we reach 100. And then we define x, y, and z. So for x, it would be 4 plus sine of 20 times t. We close dot times cosine of t. Close or apply semicolon. So take note that we apply dot asterisk, a dot product. So it would be a multiplication of corresponding points in the vector. We can also have y equal to 4 plus sine of 20 times t dot asterisk sine t. And then z is cosine 20t, 20 times t. Apply semicolon. And then to graph this, we can plot it in 3D space with the components x, y, and z. So running this would generate a space curve somewhat similar to the one in the figure. Another curve that we can trace is the trefoil knot with the equations x equal to 2 plus cosine of 1.5t cosine t, y is equal to 2 plus cosine 1.5t sine t, and z equal to sine 1.5t. So this is quite impossible. This is quite difficult to sketch manually. So again, we can have your t equal to maybe 0 with an interval 0.01 up to 100, semicolon. We can evaluate x to be 2 plus cosine of 1.5 times t, and then we apply dot product cosine t. Let's apply semicolon to that. So y equal to 2 plus cosine of 1.5 times t dot asterisk sine t semicolon, and finally z equal to sine of 1.5 times t semicolon, and then we now plot in 3D x, y, and z. You may pause this and then try to work on it in MATLAB. Even when a computer is used to draw space curve, optical illusions makes it difficult to get a good impression of what the curve really looks like. The next example shows how to cope with this problem. So use a computer to draw the curve with a vector r of t equal to t, t squared, and t cubed. This curve is called a twisted cubic. So we start by using the computer to plot the curve with the parametric equation x is equal to t, y equal to t squared, and z equal to t cubed. Now we can try the domain from -2 to 2. The result shown in the figure is shown in the figure 10a, but it's hard to see the true nature of the curve from that graph alone. So we can use t from -2. Let's have an interval 0.01 and then up to +2. Now, since the functions are simple, we can have it plot 3. And then the first point is t. The second component is t dot asterisk 2. And the third component is t dot asterisk 3. So it should be giving you this space. Some three-dimensional computer graphing program allows the user to enclose the box, the surface in a box instead of displaying it in the coordinate axis. When we look at the same curve in the box, we have a much clearer view of the picture. We can see this, that it climbs from a lower corner of the box to the upper corner nearest us and twists as it climbs. We get a better idea of the curve when we view it from different vantage points. Figure 10c shows the result of rotating the box to give another viewpoint. Figures 10d, 10e, 10f shows the view we get when we look directly at the face of the box. So we have 10d, somewhat like a parabola in the xy plane. At 10e, it is like a cubic polynomial and at 10f, it would look like a cusp. It is the projection of the curve onto the xy plane, namely the parabola y is equal to x squared. Figure 10e shows the projection on the xz plane, the cubic curve z is equal to x cubed, now it's now obvious why it is called a twisted cubic. Another method of visualizing a space curve is to draw it on a surface. So like what we have done on the helix, it is passing through um, a cylinder, a circular cylinder. So we can sketch it as it passes through the circular cylinder. For instance, the twisted cubic in example 8 lies on the parabolic cylinder y is equal to x squared. So we can remove the parameter t since x is equal to t. So we will be having y equal to x squared as we plug in t is equal to x. So from the figure, it shows both the cylinder and the twisted cubic. And we see that the curve moves upward from the origin along the surface of the cylinder. So it is a path traced along the surface of the cylinder. We also use this method in example 4 to visualize the helix lying on the circular cylinder. A third method for visualizing twisted cubic is to realize that it also lies on the cylinder z is equal to x cubed, a cubic polynomial. So it can be viewed as a curve intersecting the cylinders, the cubic cylinder and the parabolic cylinder. We have seen that an interesting space curve, the helix, occurs in the model of DNA. Another notable example of space curve in science is the trajectory of positively charged particle in orthogonally oriented electric and magnetic fields E and B. Depending on the initial velocity given a particle at the origin, the path of the particle is either a space curve whose projection on the horizontal plane is a cycloid, or a curve whose projection is a trochoid. By the way, electric field and magnetic fields are related and orthogonal to one another. They move in perpendicular motion to one another. So that's all. Thank you for watching.